We're pleased to begin the last session of the conference, and we will have Ben Elias from Oregon. He'll speak about categorification of the Hecke algebra at a root of unity.
Thanks very much. It's a great pleasure to be here with all of you here in my basement. I guess I'll start with the standard caveat. So all this is joint work with Chio, and my second caveat is that all of my iPad pens broke over the course of the last 2 weeks. So I wrote this talk with my bare hands, like a caveman, etching on the walls. So forgive me if the handwriting's not the best. Also, like a caveman, my internet here is a little bit wonky. So if you guys start going in and out, it seems like I still project well and the video of me continues, but you guys all freeze for me, and I don't know if I'm, so if I act confused, that's why. Okay. I guess my third caveat is that I'm an algebraist, not a geometer. There's been a lot of geometry at this talk, and no one has even mentioned a single Khovanov-Lauda-Rouquier algebra. That's about to change, but my talk is going to have a lot of questions for the geometers in the audience. So you'll see a bunch of big whys, and I actually want you to hold off on thinking about those questions till the end of the talk, because I'm going to give you more and more questions with more and more structure that I want you to answer for me. Okay, so categorification. In this original categorification paper of Crane and Frankel that sort of started this program in some sense, it was one of the original goals was to categorify quantum groups, not the integral form, which is what Khovanov-Lauda-Rouquier do, but quantum groups at a root of unity, in order to have some finiteness properties to crank this topological quantum field theory machinery. I'm not going to talk about that at all. But Qi-Khovanov in 2006, based on some ideas of Bernstein, suggested a practical approach to how to categorify an algebra at a root of unity. And this practical approach was then followed up by his student Chio, and now there's a bunch of papers. So I want to tell you the history of categorification of root of unity and what's been done so far. And I want to tell you why we're stuck. And to get past where we're stuck, we need some new technology. And so I want to address that new technology in the second half of the talk. It's all conjectural though. So I want to start with some common household categories if you're an algebraic categorification theorist. So there are these algebras or categories, the Khovanov-Lauda-Rouquier category, U+, whose Grothendieck group is the positive half of the quantum group. There's also this entire Khovanov-Lauda 2 category, U, which categorifies the full quantum group, not just the positive half. And then there's this diagrammatic Hecke category, which categorifies the Hecke algebra of a Coxeter group. I should have some caveats about which Lie groups are actually categorified, but I'm just not going to care about that right now. What kind of Grothendieck group am I taking here? So all of these categories are monoidal, they're additive, they're graded. So you should think of them as being like the category of projective modules over a ring. They're not abelian categories, they're just additive categories. And I'm taking the split Grothendieck group. And because of these 3 structures, I get a multiplication, addition, and a multiplication by Q on the Grothendieck group. And so the Grothendieck group is a ZQ inverse algebra. And all of these algebras here are the integral forms of these various rings. So another thing to say about these categories here on the left is that they're all presented by generators and relations. And whenever you have an algebra or a category given by generators and relations, you intrinsically have an integral form of that category. You don't have to choose your base field to be the complex numbers. You can choose your base field to be the smallest ring containing all the coefficients in your relations, and you'll get a well-defined ring. So in all these cases, you've got an integral form for your category, and that's going to be important for me because I'm going to define these categories in finite characteristic and so forth. So these categories have been studied pretty extensively for the last decade since they were invented, I guess 15 years. And one of the reasons they're very interesting is that they describe X algebras between semi-simple Purver sheaves on quiver varieties or flag varieties, respectively, for the different algebras. Now, so it came as a big surprise that while trying to pursue Khovanov's program to categorify things at a root of unity, we discovered this surprising new structure on these algebras, or Khovanov and Chio did. So the surprise is that there's secretly a differential on this category. So what is the structure that these categories have? So let me give a definition. A Gaia, which is short for a GA equivariant algebra, is going to be a graded algebra. Usually it's a parity, so it's concentrated in even degree, this grading. And it's equipped with a derivation, D, of degree 2. So it's a derivation that satisfies the Leibniz rule. But all these are monoidal categories, or two categories. So it also satisfies a sort of monoidal Leibniz rule. So this condition that I wrote down here is equivalent to saying that D also satisfies the Leibniz rule for horizontal composition and not just for vertical composition. And then the third property is that, in fact, all of these algebras are algebras over the integers. And not only do we have this derivation D, but you can actually, but D to the K is a multiple of K factorial. So you can divide by K factorial and get another operator, which is defined integrally. Okay, and one of the important consequences of this we'll see soon. But this is going to be what I call a Gaia. And it turns out that Khovanov-Lauda-Rouquier algebras, this category U+, the diagrammatic Hecke algebra, all of these can be equipped with such a differential. So let me give you an example of a Gaia. Take the polynomial ring in one variable. And the degree of x is going to be 2. So by the Leibniz rule, the differential of the identity has to be 0. But the differential of x can be some multiple of x squared. Let's normalize it to be actually x squared. And then by the Leibniz rule, you can deduce that the differential of x to the k is k x to the k plus 1. So this is your basis of the polynomial ring, and you can see how D acts on this basis. And you can then also check that these divided powers are actually well defined using binomial numbers, which are integers. So there's a great example of a Gaia. Here's the next example. So the Khovanov-Lauda-Rouquier algebra for type A1 is essentially this nil-Hecke algebra, this nil-Hecke category, which Khovanov and Lauda describe using dots and crossings. So you can think about dots as being like this polynomial ring, and crossings as being some Demoser operators. And here is just the definition of a derivation on this algebra. So I define the derivation on the generators, which are the dots and crossings, and then by the Leibniz rule that determines the derivation on all possible diagrams or elements. If you do nothing else, I mean, you can try to do some little exercises here and use the Leibniz rule and figure out how to use the Leibniz rule with diagrams. In case you've never tried to do that before, that might be something that that's helpful. So there's another derivation on the same algebra. This algebra has this category has an automorphism, an anti-automorphism, which flips pictures upside down. And the derivation that I chose does not intertwine this automorphism. So when you flip it upside down, you get a different derivation. This flipping upside down thing is, some silly diagrammatic thing, but it corresponds to duality on the category and in the category cover sheets. It's an important operation. So how should you think about a Gaia? A Gaia is kind of like a DG algebra. You take an algebra, a graded algebra, and you equip it with a differential. But since it's an even degree differential, it should satisfy a normal Leibniz rule and not a super Leibniz rule. But DG algebras are interesting. You can define their you can define the derived category and the homotopy category of a DG algebra. And so you should think that Gaia is a similar thing, and that it's just the analog in a weird version of homological algebra. But luckily, we do live in a world with that kind of homological algebra, so that's good. Now, why should there be a Gaia structure on these categories? So I said that these categories describe X algebras, and X algebras are often the cohomology of some DG algebra, but in this case, all these X algebras are formal, and there's parity involved. So there's sort of like no souped up structure that you expect to give a DG algebra structure to. You don't expect DG algebras to show up and play an interesting role for these particular algebras. And yet somehow there's this extra differential, this Gaia structure on these categories. And where does this come from in geometry? I have not yet heard a sort of a reasonable explanation. So for instance, in the previous example I gave, this is the cohomology of P infinity, or the equivariant cohomology of a point for a C star action, like why does that have this differential on it? Where does this come from in geometry? I would like to know. So that's great. But now let me tell you why Gaias are useful. So what do they give us via Khovanov's program? How do they help us categorify things at a root of unity? So first off, let me talk about Grothendieck groups. Why is the Grothendieck group of an additive category a Z module? Well, by definition, you define it to be the Z module with given by symbols of objects, right? You arbitrarily impose Z coefficients. But another way to think about this, at least to state this simply, I'm going to assume we're working over a field, is that any K-linear category has an action of vector spaces on that category. So the n-dimensional vector space acts by sort of taking multiplicity. So Kn tensor M is M tensor n, M plus n copies of n. And of course, you can do the same thing with morphisms. Matrices of scalars give you matrices of maps. So there's a sort of a categorical action of this monoidal category on A. And since the Grothendieck group of vect is Z as a ring, then you get an action of Z on your Grothendieck group. So you can think that this Z module structure is coming from this action of vector spaces. That's how I like to think about it. So if you're like to do triangulated Grothendieck groups, well, the homotopy category of A is a module over the homotopy category of vector spaces. Given a complex of objects in your category and a complex of vector spaces, you can take that tensor product of complexes in the usual way, and you get a complex of objects in A. So that means the triangulated Grothendieck group of A should be a module over the triangulated Grothendieck group of complexes of vector spaces. How do I like to think about this one? I like to think that there's a homological shift, which is giving multiplication by T. So if you just looked at chain complexes of vector spaces, then the Grothendieck group looks more like ZTT inverse. But then in the triangulated category, the suspension functor should always be -1 in the Grothendieck group. So you have to impose this extra condition, T is equal to -1, and you get Z again. Okay. But this sort of explains why the Euler characteristic appears when you're doing Grothendieck groups. And then of course, if you're in the graded setting, you've got an action of graded vector spaces on your category whose Grothendieck group is ZT2 inverse. So the reason I'm making this point is because I now want to ask the question, what base category has Grothendieck group Z adjoin a root of unity? Okay, how do I replace Q with a root of unity? So here was Khovanov's suggestion. So let H be a finite dimensional graded Hopf algebra. And I'm going to basically be assuming H is local soon. I'll give you examples in a sec. You can consider the category of finitely generated graded modules over this, which has a subcategory of finitely generated graded projective modules. And it turns out that whenever you tensor a projective module with another module, you get a projective module. That's something special to the Hopf algebra set. So this is sort of like a monoidal subcategory, an ideal. It's a tensor ideal in the sense of that last talk. And you can mod out by it and still get a nice monoidal category. So when you do, this is called the stable module category, and it's usually denoted with this nice little underline right here. It turns out this is a triangulated category. So, it's a triangulated category and a monoidal category. And when you're a local, when H is also local, so that there's so that projected modules are free, then what you're killing when you kill free modules and morphisms factoring through free modules in the Grothendieck group is you're killing essentially the graded dimension of H. So there's one simple module over H, it's the trivial module. And so when you have a Jordan-Holder filtration by that, you're just picking up your graded dimension. So the symbol of an object is its graded dimension, living inside ZQQ inverse, but then you're killing the graded dimension of the free module. And that's the Grothendieck group of this base category. So if you have then an H module algebra, then you can define in some sense, so Khovanov explained how to do this, the derived category, the H derived category of this thing. And there's an action of this stable category on this, making it triangulated Grothendieck group a module over the base ring. So to give you some examples, there's the familiar example. You take the dual numbers KD mod D squared, and you make it a Hopf algebra, where the coproduct of D is D tensor 1 plus 1 tensor D. The coproduct is supposed to be an algebra map. So delta of D had better square to 0, and it doesn't unless you're in the category of super vector spaces. This is technically a super Hopf algebra, and you'll forgive me. But what is an H module algebra? It turns out the stable category is exactly the homotopy category. And an H module algebra is just a DG algebra. So in fact, this entire theory for this particular Hopf algebra is just ordinary homological algebra. And the graded dimension of H, this free module, is 1 plus T, which explains why you have to set that to 0 in the Grothendieck group. Now, instead, let's talk about KD mod D to the P equals 0. So a module over this is a P complex. It's like a complex, but D to the P is 0, not D squared, with the same definition of the coproduct. In order for this to be an algebra map, unfortunately, we need the field to be in characteristic P. So we're going to be working over a field of characteristic P. And an H module algebra is called a PDG algebra. So this gives you a totally different kind of homological algebra, which is developed by Chio. He's basically tried to be Bernhard Keller and just rewrite all of his papers for this kind of homological algebra. And the Grothendieck group, the symbol of the free module, is exactly the cyclotomic polynomial, which lets you specialize to a p-th root of unity. What about a Gaia? So this is a module over a Hopf algebra, but it's an infinite dimensional Hopf algebra over the integers. We don't have a framework for this yet, so I don't know what to do with Gaias yet in homological algebra. I don't have a homological algebra associated to them. But if you specialize a Gaia to characteristic P, then D to the P is 0 because it was a multiple, a P factorial times something else. And so you do get a PDG algebra for each prime P. So a Gaia is like a universal PDG algebra. And the punchline is that, okay, so the Grothendieck group of P complexes is a Z adjoint of root of unity, roughly speaking. It's close enough. The precise statement is here. And this is an awesome new kind of homological algebra. And if you want to learn about that, then you should see, then you should go to Quacks, which is a conference I'm running in August, where Chio will be running a mini course on this topic, on Hopfological algebra. So as you can see, I'm supposed to have spent 15 minutes so far. I don't know when I started. How far am I in? Yeah, doesn't matter. I'm going to continue.
It's 20 minutes so far, Ben.
Okay, thanks. So I did practice, and my timing was off, I guess. Let's take, say, one of these categories, and I said that we can equip it with a Gaia structure. And we have to work in characteristic P to get a PDG algebra. So, does that categorify the quantum group at a root of unity? The normal one categorifies it over ZQQ inverse, and now I have a base ring which categorifies quantum groups at a unit of unity. Is it so easy as that? Sometimes. But it's not obvious. There's nothing for free that tells you, that lets you compute the PDG Grothendieck group. It's not. They have to do some work. So in fact, the Nilek algebra has a one parameter family of derivations, of which I only gave you two different elements of this family, D and D dual. And those are the only two which give the right Grothendieck group. All the other Grothendieck groups are some other weird thing. Okay? So something, you actually have to do work. And let me explain what the catch is, what work is. So in the category, in the KLR category, there's this object E, and E tensor E splits into two isomorphic direct summands up the grading shift. And this is something you might want in the Grothendieck group. So you might want there to be sort of a splitting of this thing into two different objects. All right, how do you do this explicitly in the additive category? Well, you construct the idempotents projecting to each of the two summands, and you have these orthogonal idempotents, which tells you that an object splits in the additive category. And Khovanov and Lauda do that for you. Here are the two idempotents, E1 and E2, and there's the identity being a sum of orthogonal idempotents. On the level of U modules, what that says is that the principal module, the representable module given by EE, splits as a direct sum of morphisms factoring through, composable with E1 and morphisms factoring through E2. And that's sort of what's happening in the Grothendieck group. This is where this computation is really happening. And it turns out that these two idempotents are also isomorphic. So both of these idempotents are isomorphic to some separate object E divided 2. Well, let's add the differential. What happens when we add the differential is that there's now a differential on all Hom spaces, a derivation on all Hom spaces. And this derivation does not preserve the direct sum decomposition. So this computation, which is the exercise from earlier in the lecture, shows you that when you take D and apply it to the first idempotent, you actually get something that lives inside the second idempotent. Of course, if you apply it to something inside this bigger module, you get some parts that live inside the first module and some parts that live inside the second module. However, the second module is preserved by the differential. So you get this sort of system right here where you've got this sort of, this is a splitting in the level of the original abelian category. It's not splitting anymore over D when you add a differential, but you've got a filtration. You've got a submodule, and then you've got a quotient module. Okay? And so you should think that when you have this filtration, you still get the right answer on the Grothendieck group. Okay? It's kind of like how a complex of object is sort of filtered by its individual chain objects, and you get that it's equal to the sum in the Grothendieck group. But this was very special to this differential. If you use the wrong idempotent decomposition, or you use the wrong derivation, then in fact, sort of neither summand is preserved by the differential, and you don't get a filtration. And this thing locks together into one big indecomposable, doesn't even have any sub-objects, D module, if you will, DG module. So you don't get the right answer in the Grothendieck group. And this is the problem, this is the catch. Said another way, it's like you were studying, take a complex and forget the differential. So just view it as an object in the additive category. That's what you used to study, and it splits into its chain objects. Hooray. But then you put a differential on it and you're like, what is this? Well, if it actually ends up being a complex, you still get the right answer on the Grothendieck group. But if the differential just goes every which way and it's not a complex, you don't get the right answer on the Grothendieck group. Anyway, so what you're really checking is some sort of statement about idempotents. You also need to get the right associated graded. You want these two things to have the same, to be isomorphic. And so you want sort of the isomorphism between them to respect this differential D. So this comes to the definition of a fantastic filtration or a finite cell filtration, depending on your favorite hobby. And this is, well, it basically is an idempotent decomposition where everything works out in the PDG Grothendieck group. There's a technical definition which isn't too hard, but I'm not going to bore you with it. Okay. So the goal to proving that your Grothendieck group is correct is showing that all the sort of tricks you used to use to get idempotent decompositions and to compute the Grothendieck group in the additive setting, that all those decompositions sort of lift to a filtration with respect to this differential. They all have to lift to fantastic filtration. That's not so easy to do. As I said before, you need to choose both the right differential and the right idempotent decomposition in order to make it work. And that really rigidifies the system. Normally, idempotent decompositions are very non-canonical. It's like splitting a vector space, a five-dimensional vector space into 5 lines. There's so many ways to do that. But in fact, there's very few ways to do it which are compatible with the differential. In fact, it's usually unique up to this duality. So that's kind of amazing. It rigidifies your situation, which is an interesting and good thing. So since we're out of time, I was just gonna... Yeah,
maybe it's a good time to take the break, or are you just gonna put the slide up? Or?
I was just gonna like skip to the end as to what's been done, and then now I'll explain this later, but I'll leave this up during the break.
Ben, do we have your slides?
Mm-hmm. They're already up
in the folder.
Okay, great.
Look, but I think they should be there. Yeah, they're in the folder. Yeah, Ben was a very well-behaved speaker and sent me the slides like multiple days in advance.
Mm-hmm.
So there was a question about what the coefficient in the if you do this d of x to the k, was it k plus L choose L times on x to the k. Was it k plus L choose?
Yeah,
K?
it was k plus L choose k, or k plus L choose L, doesn't matter.
Yeah.
Sorry, I've got to, I can do this the easy way by going to my, there we go.
Ah, okay.
Let me go read the chat now. Katerina, I will answer your question about the degree being +2 and not -2 in the second half of the talk.
Thanks, perfect.
Okay. And yeah, just with this example here, and here the Zx, this looks like to be the algebra of distributions of this additive GA, and that's first two letters of your Gaia.
Exactly.
So the D here really behaves like the tangent vector that is in the algebra of the GA, but in the characteristic P, in the positive characteristic, or even in over the integers, the algebra of distribution on this group is not the polynomial algebra; it's the divided power algebra, as you write it here.
Exactly, and that's why we called it. That's why we called it that. Let me just quickly address the statement that it's not Steenrod. So it's always degree 2. So it could be Steenrod only in characteristic 2. And it is Steenrod in characteristic 2, for what it's worth.
So maybe I missed this, but is in this example 2 and 3, is one of the differentials good and the other one not good?
They're both good.
They're both good, okay.
They're both good. They're the only ones that are good.
So how do you check that they're the only ones?
So what?
Sorry, how do you check that they are the only ones?
Right. So you can actually, and we just did this, you write down all possible idempotent decompositions for EE, and you write down all possible derivations, right? So there has to be, the derivation has to preserve the relations. So ends up being a 1-parameter family of possible derivations, and like a 2-parameter family of possible idempotent decompositions, and you just check every single thing, and you see that this is the only stuff that works. And we did this for the Hecke algebra, and we did this for the whole quantum group categorification as well.
Okay, it sounds very brave.
Yeah, it was a lot of work, but I think it was important.
Yeah.
It's a proof of concept, so.
Okay, there's no hope of translating it into something else that you can describe more easily.
Translating the computation or translating the answer? I'm trying to.
Of having some other way of producing it.
Yeah, well, that's what I want the geometers to explain to me, where this comes from.
Yeah. Okay.
I mean, ultimately, this action on the polynomial ring is not new by any stretch of the imagination, and everything is derived from that, right? Like, if you think about the Nilhek algebra as acting on polynomials, and if you equip polynomials with the differential, then it should act on Hom spaces, and this is the differential that you'd induce on the Nilhek algebra. Of course, there's a whole family of differentials, but that one is the correct one. So it's all ultimately, the action on circle bimodules 2 is just an action on polynomials. Everything is derived from this action on polynomials. But where that comes from, even in geometry, I don't know. Okay, let me see if there's a homological algebra interpretation of D. I don't, certainly it shouldn't exist in normal homological algebra because there's sort of no degree 1 derivation. It's not a DG thing. It's some other kind of homological algebra. So I don't know the correct answer to Eugene's question. Should I start again?
Yeah, I think so, if everyone's ready.
Give me a minute to get back to where I was.
Yeah.
So I'll skip a little of my talk. Let me just say, in a whole bunch of cases, we've found the right, and we've classified all the good derivatives that could possibly give you the right Grothendieck group, because they take the defining idempotent decompositions of the category and they're fantastically filtered on those. But that's still not enough to give you the right Grothendieck group, because you need to take any object and decompose it by a fantastic filtration into indecomposable objects. And that we don't necessarily know how to do. So not just the defining idempotent decompositions, but you need to be able to do enough idempotent decompositions to split objects into small enough pieces that you can handle them. And in some of these categories, those enough idempotents have been explicitly computed with great struggle. So if you look at USL2 or you think SL2, there's this Stosich formula, which is a monstrously ugly idempotent decomposition. But that's the kind of thing we had to check was fantastically filtered, and we did. But in general, idempotence inside these categories is completely mysterious. This is why for Promote and these other talks, the P canonical basis is really hard. We don't know what idempotents projecting to indecomposables look like, especially in characteristic P. But in most of these categories, we have no idea. In the Hecke algebra, it's an extremely hard and interesting problem, and it's a foundational problem with the field now. So it's kind of hopeless to use these same methods where you explicitly compute idempotent decompositions and check the fantastic filtration property. That's never going to work. So some new tool is needed. I just want to also point out that we put the right differential on this category in type A, but we also proved that there is no good differential in this category in type D and E, which is kind of mysterious. Okay. So we were trying to find some other way without using directly computing idempotent decompositions, which is very not what people like to do here, to prove that the Grothendieck group was the Hecke algebra at a root of unity. And in our search, we found some interesting new structure, which I want to share with you. So here's the next surprise. In fact, there's not just an action of a degree plus 2 derivation, there's an action of a degree minus 2 derivation. And putting it together with the degree operator, there's an action of SL2 by derivations. Okay, so this structure has been there all along, and we sort of just noticed it recently. So where does this degree minus 2 derivation come from? Well, first let me just give you the example. Degree minus 2 derivations are pretty easy to construct because most of the generators that aren't part of a polynomial subalgebra, most of the generators are in the minimal possible degree, and so Z of it has to be 0. So it's pretty easy to construct it and check that it's a derivation and to show it's unique and so forth. But the fact that it gives an SL2 action is kind of nice. So here is the polynomial ring again. So we already talked about how d of x is x squared, and we're going to do that for each variable. The degree of x is 2, so the Cartan subalgebra should act by its degree, so it should act by 2. And the lowering operator sends xi to 1 for all. And you can write, then extrapolating by the Leibniz rule, you can write these operators in sort of a nice differential operator fashion. And this is sort of a familiar thing. It's like called the Witt algebra action on the polynomial ring. You don't just have to do xi squared or xi to the 0. You can do xi to the k for any k. In all these categories that I've mentioned, there is a polynomial ring floating around inside the Hom spaces. And all these Hom spaces are actually R modules, both on the right and on the left, and they're SL2 modules, and this action is all compatible. I'll also point out that there's not like a GLN action. It's really an SL2 thing. You can't separate these different variables because in order to be a good derivation, everything needs to be SN equivariant. So you're really stuck gluing all the variables together. This is SL2. This is not SLN. Okay. So what do these modules over R, SL2 look like in practice? Here's the polynomial ring of one variable as an SL2 module. And you've probably seen an SL2 module like this before. Guess what? It's the Coverma module, nabla 0. With the gradings reversed, but that's okay. Okay? This is a coverma module. Not a verma module. And coverma modules have finite dimensional submodules and infinite dimensional quotients. So this is what the regular module looks like over R. But there's all sorts of free rank 1 R modules in this category. A free rank 1 R module does not have to have sort of trivial derivation on its generator. So if you take another free rank 1 R module with generator V, then D of it is something of degree 2. So it's a linear polynomial times V. But Z of it has to be 0 for degree reasons. And so for any linear polynomial, you can define this free rank 1 module where D of it is F. And so if A is an integer and F is like 3x, then you can check that the degree of the generator has to be degree 3 for SL2 relations to hold, and what you actually get is the coverma module nabla A. So because the degrees are swapped, nabla A is simple for A positive and has a finite dimensional sub for A negative. If you do a polynomial ring in n variables and you take a free module, the arbitrary free module has the differential of the generator being some linear polynomial times itself. And you just get a tensor product. As an SL2 module, this is just a tensor product of covermas. This is extremely infinitely generated as an SL2 module. This does not live in category O in the usual sense, but it lives in some sort of in completion of category O. And it has a finite dimensional subrepresentation if and only if all the AIs are negative. So why am I talking about finite dimensional subrepresentations, by the way? Just bear with me. There's a reason I care. So now I want to do, I want to tell you sort of a structural theorem that we were able to prove. So all the Helm spaces in these categories are free of finite rank as left R modules. This was something that was previously known in all these cases. And what we were able to do is sort of upgrade these things to say, okay, so the Helm space is split into free rank 1 R modules. And each rank 1 R module is preserved by the lowering operator Z, whereas the raising operator acts in a filtered way. So this, as an SL2 module, this has a filtration whose associated graded are these rank 1 modules over polynomial rings, which we just described all of them above. That is a filtration by things which are tensor products of coverma modules. Okay, so this is some kind of weird category O for R, SL2 modules that all these Helm spaces live in, or maybe the coverma filtered part of category O. And we can tell you what the associated graded is precisely for all the Helm spaces. Although that still doesn't make it easy to determine what the finite dimensional subrepresentations of Helm spaces are. Okay, you've bared with me. Let me give you an example. If you're not familiar with the Nilek algebra, I'll give you the punchline soon. I'm just going to quickly tell you. So the diagrammatic basis for the Nilek algebra as a module over the polynomial ring R are these two diagrams here. And you can compute exactly how things work, but you know the point is that this thing gives you a submodule, and this thing gives you a quotient module. And so there's a short exact sequence of SL2 modules whose subquotients are free with very particular associated grade. Moreover, this thing splits as an R module because I said it's free as an R module, and it also splits over this Z action because Z preserves the sum. But it doesn't split with the raising operator. But there's another way of viewing the Nilek algebra. The Nilek algebra is actually isomorphic to a matrix algebra over symmetric polynomials. So these particular diagrams correspond to the matrix coefficients in this matrix algebra. And these 4 diagrams give you a subring, which is 2 by 2 matrices over the ground field. Let's compute how the SL2 action on this subring. Guess what? This subring is closed under the SL2 action. It is a finite dimensional subrepresentation of this ginormous infinite dimensional SL2 representation. It is the maximal finite dimensional subrepresentation. Okay? Let me say this very loudly because I'm excited by it. You see, the 2x2 matrix algebra over symmetric polynomials has a Jacobson radical, which is the 2x2 matrix algebra over positive degree symmetric polynomials. And when you mod out by it, you get the semi-simplification of your algebra, which is the 2x2 algebra over matrices. But the 2x2 matrices algebra, over the ground field. But this is actually a subring. And this subring is precisely the maximal finite dimensional part of the Hecke algebra. I can see some eyes glazing over. This is extremely, extremely weird. You have never seen this before in your algebra course. You've got this sort of standard sequence where you take the Jacobson radical of a ring and you include it inside a ring, and the quotient is semi-simple. And this is a short exact sequence of R modules, which is not preserved by the SL2 action, because this is not an SL2 module. This is not preserved by the lowering operator. But then you have a section of this thing. This thing is split on the level of vector spaces. And so you have a section back, the inclusion of this as a subring inside here. And that is a short exact sequence of SL2 modules. This is an SL2 submodule. So this is not a it's not an ideal, it's a subring, not an ideal, but it is an SL2 submodule. And this is an ideal, but it's not an SL2 submodule. And so you've got these two short exact sequences which split each other. So to say it in a different way, the finite dimensional part of this SL2 representation is a complement of the Jacobson radical in this example. I mean, I don't know, if anyone's ever seen anything like this before, I would love to hear from you. But this has like intense applications to the structure of the category. It lets you play the SL2 action against the structure of the category and sort of try to use finite dimensional representations to see how things split. I'm going to give you another example, although it's the same example.
I think Monica has a question.
Okay.
Yeah. So just going back just because I think I missed or need to be reminded. So yeah. So this not quite rightmost blue arrow from 2x2 matrices over K into 2x2 matrices. Yeah, that one there. Yeah. What's the image of that again? What?
That's just the inclusion of this subring generated by
the subring that had in the upper right hand corner. That one there. Okay. Yeah. Great. Thanks. Yeah.
So how do you understand decomposition of objects in a category? A typical way is using local intersection forms. So let me do this in an example. In the Hecke category, there's an object BS. And when you tensor it with itself, you again get two copies of BS. This is just like the example kind of I was doing before, although it's slightly different. So, well, if you want to construct this decomposition, you need to choose two inclusion maps and two projection maps corresponding to these two summands, such that when you compose them, you get the identity or zero of this summand. So in general, if you've got sort of an indecomposable object and you want to compute its multiplicity in something, you take the space of all possible inclusion maps and the space of all possible projection maps, you compose them to get an endomorphism of an indecomposable. That's a local ring. You can mod out by it to get, in this case, the ground field. And this gives you a pairing between the maps in and the maps out, which is called the local intersection form. So the multiplicity, so if you have dual bases for this pairing, then they give you sort of orthogonal inclusion and projection maps, which construct explicit direct summands inside your big object. This pairing isn't necessarily non-degenerate, but the kernel is precisely the Jacobson radical, at least where it intersects this particular Hom space. And the rank is the multiplicity of this indecomposable as a summand. So if you take this Hom space of possible inclusion maps, say, and you mod it by the kernel, this is some way of describing, in some sense, the multiplicity space, which is the multiplicity of your irreducible indecomposable object inside your category. But it's naturally a quotient. It's not a submodule of your Hom space. I'm calling it the local intersection form and not the local intersection pairing because there is this duality functor which gives you an isomorphism between these two Hom spaces. So it's really, you can consider it as a form on the space of projections or a form on the space of inclusions. So this Hom space is a free module of rank 4 over R. It's an enormous infinite dimensional vector space. But here is the unique element in degree -1 in the diagrammatic physical bimodules, which you don't have to care about. And if you just compute what happens to this under the SL2 action, for graded reasons, it's killed by the lowering operator. It has nowhere to go. And d of it is this thing, and d squared of it is 0. Holy cow, it's in a finite dimensional subrepresentation. There is no reason that should be true. Okay? And if you look at this finite dimensional subrepresentation, you have right here 2 possible projection maps. Okay? So the finite dimensional part of this Hom space is a complement to the Jacobson radical. And it gives you sort of the multiplicity space now appearing as a sub of all the Hom spaces rather than a quotient. It's sort of a canonical section of the multiplicity space. It's just extremely weird, extremely weird. Moreover, you have the Hodge-Riemann bilinear relations with respect to this local intersection form. So in this silly little example, which is very small, if you take this particular projection map, flip it upside down to get an inclusion map, and pair it against the differential of itself, you get a positive sign. The plus sign is supposed to be the Hodge-Riemann bilinear relations. Okay, this example is too small to witness the Hodge-Riemann bilinear relations if you know what those are, but you can do much bigger examples and you get the Hodge-Riemann bilinear relations in all the examples I've computed. This is some new kind of Hodge theory on multiplicity spaces, which I've never heard of before. So the way I've been describing it is a little bit too naive, because you go to sort of the next interesting example, and it's not true that the finite dimensional part is a complement to the Jacobson radical, but almost. So this object has 2 direct summands, and so the complement of the Jacobson radical and the Homs out of X, in decomposables should be 2-dimensional. The finite dimensional part is just 1-dimensional. But if you take the finite dimensional part and then you act on it by the category, so you act on it by the category to get a submodule, and then you quotient by out by that, it then has another finite dimensional part again. And that's where the remaining 1-dimensional piece is. So if you take the finite dimensional part of your SL2, you act by the Jacobson radical, you kill all of that, you take the finite dimensional part of what's left, you act by the Jacobson radical, you kill all that, you take the finite dimensional part of what's left, and when you're done, you have a complement to the Jacobson radical. That is this conjecture that's true in all the examples that I've found, although not quite the Jacobson radical, it's more complicated than that. So skipping ahead, ignoring the part about the Kashiwara-Saito singularity, in conclusion, I do have some conjecture which encapsulates this weird behavior in the interaction between splitting in the category and the finite dimensional part of the SL2 representation, but it's extremely technical to state because the real life is complicated. However, what it tells you is that the finite dimensional SL2 parts in some in Hom spaces are sort of sufficient to construct enough idempotents to take an arbitrary object and decompose it into irreducibles and indecomposables. And because of this SL2 nature, these filtrations are sort of built in. The filtration with respect to the raising operator is built into an SL2 module. And so that gives you the right statement on the Grothendieck group that you'd want. Moreover, there's some new kind of Hodge theory, which is not really quite clear. And yes, that's all I wanted to say. Oh, yes. So a Hodge theory for multiplicity spaces has already been developed by myself and Williamson, although this is the quotient version, and it uses a completely different Lefschetz operator than this weird derivation, which is some new thing. So the relationship between these two kinds of Hodge theory is completely unclear. Okay, thank you. Sorry for going over.
Okay, thank you. If anyone has some any questions, please unmute yourselves and ask away.
Ben, you weren't over. You had like 3 more minutes.
Oh. My apologies. Oh yeah, you're right. I started late. I forgot about that. Oh well. Let me talk about the Kashiwara-Saito singularity. This is the first time that something goes wrong in finite characteristic. It's an S8 with some element that's pretty close to this one right here. Okay. So in there's this Bott-Samuelson corresponding to this reduced expression. And in characteristic 0, this Bott-Samuelson splits into two indecomposable objects. One of them, it has a lower summand corresponding to this element right here. But in characteristic 2, this is indecomposable. So in this example, it turns out that sort of the projection map from W to Y and the inclusion map, these do not live inside finite dimensional SL2 subrepresentation. So there's sort of no way in this SL2 world or in the PDG world to make this thing sort of a sub or a subquotient of this thing. Which is to say that the fact that it splits in characteristic 0 is something of an accident. This doesn't ruin my conjecture, but it sort of means that there's this sort of like SL2 canonical basis, which is separate from the P canonical basis and separate from the Angelo-Lustig basis and so forth, which records the SL2 indecomposable summands. And that maybe this SL2 action also detects P torsion, although many more examples would have to be done before that could be made into a conjecture.
So is there any meaning of the weight spaces for this SL2?
It's just the usual degree.
What's the usual degree? Okay.
There's a question from Elijah. Do you want to just ask your question, Elijah? Let's unmute yourself.
Sure, yeah, I thought it would be easier for him to read. Your process of taking finite dimensional submodule and then applying Jacobson radical, is that always 2 steps, or you just do it over and over and over again?
You just do it over and over again, but it should be a finite number of steps.
So you said that this SL2 action interacts nicely with the left action of R?
Yeah.
Interact nicely with the right action of R as well?
Yeah. That comes from the monoidal structure. It's a monoidal thing, and the R is the monoidal endomorphism, the identity, I guess, in the Hecke category context.
But like if you split it like as a free left R module or as a right R module, does it give like some kind of relation?
The filtrations get reversed. Or like let me phrase it this way. If you're thinking about modules over the category, so like to an object in the category, you should think that you should think about that as corresponding to a left module by taking Hams out of that object, or as corresponding to a right module by taking Hams into that object. And so idempotents will sort of give you either left submodules or right submodules, and the order on this filtration is reversed when you swap these two contexts. So that's not really having to do with the action of R on the right or left, now that I think about it. Although in the context of Hecke algebras it is, because you're asking about top or bottom.
So of these conjectures that you mentioned at the end, can you just go back to it? This conjecture, the conjecture which is technical to state. So that will imply the desired result about this.
About the Grothendieck group, yeah.
Grothendieck group, and also will it work? But this is in what settings?
This conjecture is really sort of some statement about what's happening integrally, but it should imply, it will imply that if you specialize to characteristic P and take the PDG Grothendieck group, that you get the Hecke algebra at a p-th root of unity, or a 2p-th root of unity technically. That is conjectural. Even this implication is slightly conjectural, because what basis do you get? Like, what is the basis of indecomposable? It's a triangulated category, so you have to be a little bit careful what you're saying. But basically, I claim that inside a Bott-Samuelson for a reduced expression, that there's sort of a unique top summand that is sort of a submodule, or that appears in a subquotient in some sort of filtration. It's not always a submodule, the top quotient. And so that is conjectural as well.
But will it work also in the KLR setting?
Yes.
Conjecturally?
It should work. Yes, it should work in the KLR setting, hopefully. I mean, again, there's some conjectures that underlie a lot of these things. But so this conjecturally, both statements conjecturally imply each other. I believe that this, in the presence of an SL2 action, having the right Grothendieck group is basically equivalent to my conjecture, which is how I came upon it in the first place. But there's a lot to be done. I just really want to know if anyone in geometry can explain the SL2 action. Again, this is like the distribution algebra on SL2 acting on these rings. Why is that the case?
So why do you restrict to type A for the Hecke algebra?
Yeah, so it's pretty interesting. I mean, it's a bunch of just computations, but the outline of it is kind of weird. So if you look at BS, BT, BS, it's supposed to have BSTS and BS as summits. Well, which one is the sub and which one's the quotient? It turns out that, this is a choice based on, there's two choices of D that work, dual to each other. And with one choice, STS is the sub and S is the quotient. But then if you do BT, BS, BT, it's the other way around. BT is the sub and BSTS is the quotient. And you can encode this in an orientation on the Dinka diagram. And in order for you to have the right Grothendieck group, your Dinka diagram has to be sort of consistently oriented. So type A just has to be oriented from left to right. And there's no way to consistently orient type D for all the type A substrings. So I don't have a good conceptual explanation. This is all like, there's something special in the geometry of type A, but I don't know what it is.
And the Hecke algebra here, you can be at the roots of a unit at any order, but here it seems to be just a...
So this is the limitation in what's known about Hopfological algebra at the moment. So I gave you an explicit way to categorify Z adjoint a pth root of unity. But I didn't tell you how to categorify Z adjoint an nth root of unity. So there's a recent paper of Qi and Lawitz, which sort of tried to construct the base category, which categorifies an nth root of unity. Although that hasn't yet, the next step would be to apply that by putting that structure on the KLR algebra, and that hasn't been done yet.
And you use the weight D algebra as a motivation, and it seems that you're using just the differential operators, using degree -1, degree 0, and degree 1. But also there are higher order operators like x cubed multiplied with a differential operator.
Right, although these are related to divided powers, aren't they?
In this case, yes, these are all vector fields. And what I'm trying to see that I saw some kind of a shadow of this SL2 in the conformal structure in the conformal field theory, at least from a vertex operator algebra, and that's where the Versoradi algebra, where the one of the differential operators that L -1 that's automatically always inside any of those any vertex algebra, and the degree 0 parts and another parts. Right. That's the Z you are adding here. That may not necessarily be there for every conformal field theory, but the L -1 in the VOE case, that's always there. So I don't know how they are related in this sense.
That's very interesting, though. Thank you. I'll have to. Great.
Are there any more questions?
I have a quick question. So Khovanov had a paper about with algebra action on not homology. Is it the same?
Right. Yeah, he actually technically constructs the positive half of the Witt algebra, which doesn't have the Z. I don't know why you left it out. In his paper, he just did the positive Witt algebra, but yeah, absolutely. So it's the same action. It's absolutely the same action. So this action is not new, but the sort of application to computing Grothendieck groups and that sort of thing.
I have a possibly silly question, Ben.
Yes.
Hey, it's Monica. Here, I can put my video.
I know.
So I think I'm trying to absorb this. I'm getting a little bit lost about where things are living, and of course we're categorified and everything. But so when I think about Hecke algebra at I guess that symbol there is to me for a p through of unity. Is that what?
Yes. Yeah.
So right. So I mean, like, so the blocks of that are parameterized by p cores or partitions of n. And so do you see, when you say enough idempotents, do you mean like, as many as corresponding to p cores? That the block
No. This is a different categorical level. So I just mean like one for every. So you can take a Bot-Samuelson object, which is associated to an expression in the symbol reflections, and decompose it into indecomposable objects.
Okay, so it's more, but then
it's sort of like one for every element of the wild group.
Okay.
Like a basis of the Hecke algebra.
But then, is there anything? I mean, given that the Hecke algebra does decompose into blocks,
that's more related to like p cells and things.
And what does that look like on the other side?
Right. So I mean, again, like to do anything at a p through of unity, we need to be working in characteristic p under the current prevailing Hopfological algebra that we know how to use, which is kind of a limitation, but what are you going to do? And so the cells that appear in that context give you sort of categorical representations, although it's not like the categorical representation theory in finite characteristic hasn't been as developed as it is in characteristic zero. So I mean, I can't tell you for sure that p-cores and everything show up. I really don't know.
So Ben, I mean,
the cell theory is not enough, actually. Sorry, cell theory is not enough to get down to the irreducibles. You have to do something more interesting. Sorry. So I'm not sure the answer to your question.
I mean, you should be able to use these like categorified Jusis-Murphy elements and categorical diagonalization to find out something about I mean, that's somehow where...
No, but see, categorical diagonalization, that theorem of Matt and I, works in characteristic zero and does not work in characteristic p. The characteristic p setting is considerably more interesting. And so it shouldn't work in characteristic zero with this extra action either. There's more eigenmaps corresponding to the p cells. I believe now there should be more eigenmaps corresponding to the d cells. And the categorical diagonalization theorem is quite different.
Okay.
It's pretty interesting.
But I mean, somehow one way to interpret Monica's question is, well, okay, maybe there isn't sort of a good version of like diagonalizing the full Jusis-Murphys, because we know that doesn't work very well in characteristic P, but there is this p-core decomposition that comes from looking at the generalized eigenspaces of symmetric polynomials in them.
Mm-hmm.
So can you find some good interpretation of that?
Yeah. So, in fact, I think I already, in fact, that is probably the interesting extra subtlety. Let me just think. I only know examples in type B, because in type A, to get anything different in characteristic P takes a long time. That's probably not true on the Grothendieck group, but in the...
Oh, Ben, I mean Ben Webster. Can you explain me how the block decomposition, so that means decomposition with respect to symmetric polynomials in Jusis-Murphys, can be categorified? So what are the symmetric polynomials in Jusis-Murphys on the categorified level?
That's a question to the other Ben.
Oh, that's the question to the other Ben, okay.
Well, I only know the full twist is the one that you know really well. The other symmetric polynomial is like this. The first symmetric polynomial is this really hard thing to construct that Korsky and Guth-Rasmussen want you to construct.
Okay, full twist I understand. Okay, good.
But the full twist, that's categorical diagonal as well. And it's still true in finite characteristic. It's just that there's more eigenmaps and more eigenvalues and more cells.
Yeah, well, that's
I can't prove this,
okay.
but it's still true.
Okay.
Wait, why is it still true?
Just based on one calculation in type B2 and G2. That's what I'm basing this on. All right. No, in type A though, the P cells are the same as the normal cells. So you have to start going to type B before you're going to get anything interesting happening.
Well, I mean, you still have like, the block decomposition gets more complicated in type A very quickly.
Right. And that could possibly be reflected in the indecomposable decomposition, and this D-canonical basis. I don't know. So the problem is that something already goes wrong in the P-core business in characteristic 2 for S4, right? Like S4 already has some interesting stuff going on. Is that true?
Well, S2 over F2 has an interesting block decomposition, right? Right.
Well, so here, well, yeah, so in this case, you can see something happening in the PDG Grothendieck group. Because I'm trying to, my laptop locked itself, so I can't scroll. In this decomposition of BS into BS plus BS, it turns out that BS tensor BS is actually contractible when you're in characteristic 2 or at a fourth root of unity. Sure. So this decomposition isn't something that's in the Grothendieck group.
Well, wait, I mean, over F2, B squared is 0. Yeah.
Sorry.
But like,
just make sure I have this statement correct. No, this isomorphism still holds in the Grothendieck group, but it just tells you that the object is contractible.
Yeah.
Sorry. It's in Khovanov-Lauda land, it's different.
But I mean, somehow if you want to see two interesting blocks, you should go to S3 in characteristic 2.
Right.
Because then there's
nothing particularly interesting happens in S3 in characteristic 2, as far as I can tell.
Okay. But, like there's the sign and the trivial. And yeah, those are the only irreps.
Yeah, and right. Don't know what to say.
No, wait. I'm crazy. We're in F2.
There's 3 cells.
Trivial are the same, but
I don't see any any relationship between sign and trivial in that case.
No. Sorry. There's there's another block which is isomorphic to that one. Thanks.
So can you explain again your calculations in the Sorge bimodules diagrammatics?
I didn't write down the differential on the Zergel calculus, but you can find it in the paper that's on the archive.
Okay.
So D of a trivalent vertex puts a polynomial below the trivalent vertex, or D of this trivalent vertex puts a polynomial right here in the middle, and D of a dot puts a polynomial with a plus sign.
And what is the second picture?
So this picture right here is the differential of this one.
Okay.
So if you have a derivation on the category, so you have an interesting operation on complexes, right? Because if you have a complex, you can apply derivation to each differential and get an interesting and the funder of the complex. So what does it mean?
That's an interesting question.
Here on complexes?
It's sort of like, so the way that I think about it is, well, I mean, I like to think that this SL2 structure is what's replacing complexes. Like you shouldn't be using normal homological algebra. You should be using some sort of other kind of homological algebra where this raising operator is the differential, so which both has an internal and an external part, like a DG module.
No, I guess I'm asking.
But your statement is still correct that given a complex of these things, probably you should be able to hopefully extrapolated into some big giant SL2 module, which you should be studying. But again, the right kind of Grothendieck group of this is unclear.
No, I think I'm asking much easier thing. So if you know that d squared is equal to 0, then apply derivation. You have like derivation of d times d plus d times the derivation of d. That's 0.
Right. Okay.
And so this means the derivation
your chain map.
is an end fund. Is it like a chain map on complexes?
Right. That's cool.
So this is like abstractly action of like first Hopfological homology, whatever.
Nice. Okay. Cool.
But like, so this means that every complex has a canonical endomorphism or something like this?
Guess so.
Yeah, I mean, also in first social homology, the degree derivations are like a Cartan part. I mean, everything has a weight space decomposition with respect to that. So, yeah. I mean, I've been wondering also with my previous question how to. I mean, I didn't quite get like how you really relate then the idempotent and the derivations and try to identify those derivations that work for you. But maybe really there is some way of working in first social homology.
I can write that down for you. It's pretty easy. So like, if you have a bunch of idempotents EI such that the sum is the identity, what you want is a partial order on the indexing set such that D of EI times EJ is 0 for I less than J. Less than or equal to less than. This is what like a DG filtration is basically. You can ask the same question about DG algebras. But actually what I'm more interested in is you have a collection of inclusion maps and projection maps. And there I want D of IJ composed with PK to be 0 for J less than or equal to K. This is the fantastic filtration. So that's all I'm asking.
Hey,
Okay.
Ben,
Yeah,
I think we better prepare now for the next.
Yes, please.
Great. Oh, and there it is.